Hello. In the last few of these videos, we have engaged with this business of calculating canonical partition functions for various model systems. In particular, the last video considered the ideal gas molecule. The essence of that video was that we introduced the following Hamiltonian and said that this described a system of n non-interacting particles that were not sat on a lattice. In other words, this was an approximate model for the atoms in a gas of noble gas atoms. We showed that when we performed the integrals required to calculate the partition function for this system was given by the expression shown here. We then showed how by taking suitable partial derivatives of this expression for the partition function, we could recover the equation of state for the ideal gas that had been discovered through experimentation. On top of this, in the exercises, you should have extracted an expression for the average energy of the atoms in the gas, and then use this expression to show that the constant volume heat capacity of an ideal gas is constant. Throughout all of this, we have taken pains to refer to the model system under investigation here as an ideal gas. We have done so because the behavior of real gases deviates from the laws described on this page. In this video and the next, we are going to look at why there are these deviations and how we can create more realistic models for gases. Let's start with the question of why deviations from ideality arise in real gases. There are three important assumptions that we made in the derivation of our ideal gas partition function, and the first should come as no surprise to you, as I stated that we were assuming it outright in my previous videos. We assume that there are no interactions between the particles that make up the gas. Now clearly this is not true, as there are interactions between atoms and molecules in general. If there were not, we would never observe the formation of solids or liquids. Everything in the universe would be gaseous. Having said that, however, the interactions between the particles that make up a gas are usually weak. And so, when we model gases, this turns out to not be such a bad assumption. The second assumption that we made when we did our ideal gas model was that we assumed that the gas was composed of zero-dimensional point particles. In other words, we assumed that atoms and molecules that make up the gas have no internal structure. This is clearly untrue. Even an atom is composed of a nucleus and electrons and has lots of internal structure. If our model is to be more accurate, we should include more of this fine structure. The final assumption that we made is that we assumed that the particles that make up the gas behave classically. In actuality, we should use the more accurate tools of quantum mechanics in order to describe the motion of these particles. In this video, we are going to focus on the issue of how to incorporate the internal structure of the particles that make up the gas in the Hamiltonian. Before we get onto that, though, it is important to note that real gases have all of these three features simultaneously. There are weak interactions between particles, the particles of which the gas is composed have internal structure, and the particles of which the gas is composed should be described using quantum mechanics. When we see deviations from ideality, it can thus be difficult to ascribe the deviation to one particular approximation in the ideal gas model. An advantage of modelling and theory over experiment, then, is that we can incorporate these effects one at a time into our model, and we can investigate how each one in turn affects the behaviour of the gas. From modelling like this, we can thus learn that quantum effects are not so important when the system is at a high temperature. Similarly, and perhaps rather obviously, the deviations due to the internal structure of the particles that make up the gas is less for noble gases than, say, for oxygen, which is composed of O2 molecules. At the same time, if we understand how the macroscopic properties of molecules can be calculated based on the microscopic interactions between atoms, we can begin to understand how we can extract information on the microscopic interaction potential, the internal structure of the molecules, and so on from experiments that measure macroscopic properties. This business of understanding the deviations from ideality is thus very important. With that in mind, let's look at how we can start to create statistical thermodynamic models that incorporate the effect of the internal structure of the particles that make up our gas. To better understand how we might go about doing this, let's consider a trick that we have used extensively when examining all the model systems we have looked at thus far. In all those videos, we have seen that if we have a Hamiltonian, like the one shown here, which is a sum of terms that each depend on different coordinates, then the expression for the partition function of this model looks something like this. When we have encountered integrals like these ones elsewhere in this course, we have always started by rewriting the exponential of the sum as a product of exponentials, as shown here. We have then seen how we can separate the integrals or summations, as each of the exponentials in this product depends on only one or two of our integration variables. The consequence of all this has been that if we have a Hamiltonian that consists of a sum of terms, such as the one at the top of this slide, then the partition function corresponding to that Hamiltonian will be a product of individual partition functions. It turns out that this trick is invaluable when it comes to calculating the partition function for a complex object like a molecule. With that in mind, let's now consider the simplest molecule we can think of, a diatomic such as N2, O2 or F2. To make our little life a little bit simpler, we're going to suppose that it is confined in 2 dimensions in this video. In reality, our molecules can obviously tumble around in 3 dimensions. The arguments that I'm going to talk through here, though, will all be very similar if we go into 3 dimensions. Now suppose that we have to tell someone where the atoms in our molecule are and how fast they are moving. In other words, suppose that we have to specify the microstate that our molecule is in. How many numbers are we going to need to provide in order to specify our molecule's position and velocity? Well, obviously, we are going to have to provide one number that tells us where along the y-axis the first atom in our molecule is, and a second coordinate that tells us where this atom is to be found along the x-axis. We are then going to need 2 additional numbers to tell us how fast it is moving along these 2 numbers. Furthermore, we are going to have to do the same thing for the second atom in our molecule. We are going to need here to provide an x, a y, a vx and a vy coordinate for this atom also. We thus need to provide 8 numbers in order to specify the coordinates of the 2 atoms in a diatomic. In physics, we call these various coordinates that we need to specify the degrees of freedom in our system. We thus state that our diatomic molecule has 8 degrees of freedom. In general, a system of n atoms in a real 3-dimensional space has 6n degrees of freedom. An x, y, z, vx, vy and vz coordinate for each of the atoms within the system. Importantly, it turns out that providing an x, y, vx and vy coordinate for each of the atoms in the system is not the only method we have for specifying the positions of the atoms in the system. We can instead adopt different methods for specifying all the coordinates. We might, for instance, specify the position and velocity of the centre of mass. When we do this, and we change either of these 2 position coordinates, the molecule moves around rigidly, so we thus still need more coordinates. In particular, we need a coordinate that tells us about the angle between the vector connecting our 2 atoms and the x or y axis, along with an angular velocity for this coordinate, so that we can incorporate rotation of the molecule as shown here. Furthermore, we need to consider changes in the length of the bond connecting the 2 atoms, so that we can stretch and compress the molecule. In total then, even with this different system of coordinates, we still require 8 numbers in order to specify fully the location and velocity of both the atoms. Furthermore, a rule similar to this holds for all systems. If we have 6n degrees of freedom, 6n coordinates are required in order to fully specify the coordinates of the atoms in the system. We can change precisely what these coordinates tell us about the systems, but we cannot decrease the number of coordinates without losing information on the microstates. What, you now may ask, is the point of all this changing the way that we represent the microstate of the system? Why do we not always use the system that I specified at the start, where you have a set of 3 Cartesian coordinates and 3 Cartesian velocities for each of the atoms in the system? The answer comes when we consider how to construct the Hamiltonian for the system. If we think about the second coordinate system that I introduced, we have 2 coordinates that describe translational motion of the rigid molecule. We know how to use Newton's law of motion to describe a rigid object moving about, and so we know that we can construct in our Hamiltonian to describe this rigid motion. Furthermore, when we do this, we realize that unless there is some external field, the x and y coordinates of the centers of mass do not enter the Hamiltonian, which is why we simplify matters and reduce the number of degrees of freedom in this Hamiltonian by 2. The second coordinate we introduced described the rigid rotations. Classical mechanics also has a large number of equations that can be used to describe rigid rotations around an axis. We thus once again know how we might incorporate a term in our Hamiltonian that describes the motion, that describes this motion. Furthermore, as with the translational motion of the center of mass, the position coordinate for the rotation does not enter the Hamiltonian. Only the rotation velocity enters the rotational Hamiltonian. Last of all, we have the extension and compression of the bond. If we assume that the bond behaves like a Hooke's law of springs, you can use that staple of physics, the simple harmonic oscillator, to incorporate motion along this coordinate in our Hamiltonian. For vibrational motion, we will need to specify both the velocity and the position coordinate in the Hamiltonian as the potential energy term, unlike those for the center of mass motion, and rotational motion is not 0 everywhere. In short then, we use these translational, rotational, and vibrational coordinates to describe the microstate the system finds itself, instead of a set of Cartesian coordinates centered on each of the atoms within the system, as when the coordinates describe the translational, rotational, and vibrational state of the system, it becomes more straightforward to construct a Hamiltonian to describe the behavior of the molecule. We can write the Hamiltonian as a sum of a translational, a rotational, and a vibrational part, as shown here. Furthermore, we state that the number of degrees of freedom for the system is equal to the number of parameters in the Hamiltonian. So in general, an n-atom molecule in 3-dimensional space will have 6n minus 6 degrees of freedom in total. Within the Hamiltonian for such a molecule, there will be 3 parameters for the translational degrees of freedom of the center of mass, 3 parameters for the rotational degrees of freedom, and 6n minus 12 parameters for the vibrational degrees of freedom. Let's now think about how we might calculate the partition function for our diatomic. Inserting the Hamiltonian that we just arrived at into our expression for the partition function, we get the following. I have written the sum over microstates here using integral signs. The first of these integrals runs over the values the x-coordinate of the first atom can take, while the second runs over the velocities that this atom can take along this axis. The third of these integrals then runs over the value the y-coordinate the first atom can take, and the fourth, the velocities along this axis. The 5th to 12th integrals then run over the x and y, vx and vy coordinates of the second atom. The important thing, though, is that we do not necessarily have to integrate over these Cartesian coordinates. We can instead integrate over the coordinates that describe the translational, rotational, and vibrational state of the system. The coordinates in this second set are, after all, just nonlinear combinations of the x1, v1, x2, v2, x3, v3, x4, and v4 coordinates that we have just described. We can thus substitute the integration variables and convert the integral for something that looks impossible into something that feels tractable, as shown here. This integral is tractable because we can, as always, rewrite the exponential of the sum as a product of exponentials. Furthermore, each of these exponentials is a function of the subset of the coordinates, and thus the integral is separable as shown at the bottom of the slide. It turns out that we can calculate each of these integrals separately. We do the first by considering a model system that has only translational degrees of freedom. In fact, we have already seen how to do this one. This is just the partition function for the ideal gas. To calculate the second integral, meanwhile, we can consider a system that has only rotational degrees of freedom. This is also straightforward, and you'll see how it's done in the exercises. A similar thing holds for the final integral. In the exercises, you will learn how to calculate the partition function for a harmonic oscillator so that this can be inserted here. What we therefore find is that we can calculate the partition function for the diatomic molecule by taking the product of partition functions that describe model systems that have only translational, rotational, and vibrational degrees of freedom. Furthermore, once you understand how the translational, rotational, and vibrational partition functions are calculated, you can use these same expressions when calculating the partition function for any molecule. To summarize then, we have in a previous video introduced the ideal gas model, which makes various assumptions about the particles that make up the gas. Namely, that they don't interact, they behave classically, and that they have no internal structure. In this video, we have looked at how we can incorporate the internal structure of the gas molecules in our model. We have seen that the first step in doing so involves writing the Hamiltonian for the molecules that make up the gas as a sum of translational, rotational, vibrational, and electronic components. When we write the Hamiltonian in this way, we find that the partition function for the gas becomes a product of translational, rotational, vibrational, and electronic parts. Importantly, this all assumes that there is no coupling between these various degrees of freedom. Normally, though, it is reasonable to assume that the rotational motions and the vibrational motions of the molecule are not strongly coupled, and that this factorization of the partition function is thus valid.